Hello everyone, myself Dr. Ramgopal, working as Associate Professor in Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to the today's session on limit and continuity of a function of complex variable. So this concept comes under the course Vector Calculus and Complex Analysis. And today I am going to discuss about the following. The first one is limit of a function of complex variable. So how we define the limit of a function of complex variable. Next, continuity of a function of complex variable. When a function is said to be a continuous function, that we are going to discuss. And also the derivative of a function of complex variables and conjugate of a complex variable. And then I'll solve some problems on the same. Now first, what is a complex variable? For example, if z is in the form x plus iy, where x and y are real, this z is called a complex variable. Z equal to x plus iy. And if you consider any function with such variable, for example, f of z, that is called a function of complex variable. Now, we are going to discuss what is the limit of this f of z and when it is said to be continuous and how to find the derivative of this function and also the complex conjugate of a complex variable. Now the first one is limit and continuity. Let us consider a function f of z. Now we need to find the limit of this function as some. For example, here we know that this f of z is also denoted by w, which is a complex variable. So w is f of z. A function w equal to f of z is said to tend to a limit L as z approaches z naught. That means as z approaches z naught, z is reaching z naught, this f of z reaches the limit L. That is the actual concept. As z tends to z naught, this f of z tends to L. In which way? For every real epsilon, we can find a positive delta such that modulus of f of z minus L is less than epsilon. So, what is the meaning of this? F of z, our function, and L is the final limit. The difference between these two is less than epsilon. Now, what is this epsilon? In general, we consider epsilon as the smallest positive integer. So, to denote the smallest positive value, epsilon is the smallest positive value. The difference between f of z and L is less than a very smallest positive value. That means there is no difference between these two. We can write f of z equal to L. But we cannot denote directly like this. So that's why we introduce this limit concept, and as limit, now when this happens, f of z equal to L, when z tends to z naught. So limit z tends to z naught f of z is L. This is the definition of limit and the notation also. So limit of a function if exists, that is unique, and it is denoted by limit z tends to z naught f of z equal to L. So simply the difference between f of z and L is lesser than a very smallest positive number. Here epsilon itself is the smallest positive number and the difference between these two is much more lesser than that. So what does it mean? These two are the same. So as z tends to z naught, this f of z tends to L. That L is called the limit of the function. Coming to the next definition, continuity. Continuity of a function f of z. A function f of z is said to be continuous at a point z equal to z naught if first f of z should be defined and also the limit as z tends to z naught, f of z must be equal to f of z naught. So this is a definition of continuity or continuous function f of z. So here we have the function f of z and the point z equal to z naught, and also we are finding the limit. Now, as limit z tends to z naught, f of z, this value must be equal to, if you substitute this z naught in f of z, what we will get? F of z naught. So these two must be the same. These two should match. So limit z tends to z0, f of z equal to z0, f of z0, then the function is said to be a continuous function. Similarly, the next definition, derivative of a function of complex variable. Let us consider f of z. Let us suppose this function is defined for all z in the neighborhood of z0. Now, if limit delta z tends to 0, f of z0 plus delta z minus f of z0 by delta z, this limit exists. If this value exists, then the function f of z is said to be derivable or differentiable at z equal to z0, and which is denoted by f dash z0 and is called the derivative of f of z at z equal to z0. So, how we define this derivative? Simply, let us consider the difference between f of z0 plus delta z minus f of z0. So, this delta z is the difference or the change in the z by delta z, as limit this delta z tends to 0. Let us find this value. If this value exists, then the function is said to be derivable at the point z equal to z0. Simply derivable or differentiable, and which is called the derivative. And simply, if you substitute z minus z0 is delta z, then what is the value of z? Z0 plus delta z. So, z equal to z0 plus delta z. Then z0, we can replace this z0 plus delta z by z. So, f dash z0 is equal to limit f of z minus f of z0 by z minus z0. This gives the derivative of the function. So, this f dash z0 is the derivative of the function at z equal to z0. How to find this derivative? Simply first find the difference between the function f of z and also at the point z0, f of z minus f of z0 by z minus z0, where z tends to z0. So, this gives the derivative of the function f of z at z equal to z0. Now, the next one is conjugate of a complex variable. So, let us consider a complex variable z equal to x plus iy. This is a complex variable. Now, the conjugate of this z is denoted by z bar. And how we get the conjugate? Simply replace I by minus I. So, therefore, z bar will be, here I is replaced by minus I. So, x minus iy. Similarly, if z is x minus iy, what will be z bar? Replace I by minus I. So, here we get plus iy. Similarly, we can calculate the conjugate of complex values also. For example, we have some z1 equal to a plus ib. Then, what is its conjugate? A minus ib. So, 2 plus 3i. What is its conjugate? Replace I by minus I. 2 minus 3i. I minus 2. What is its conjugate? We need to replace I by minus I. So, minus I minus 2. For example, we have 3i. What is its conjugate? Minus 3i. And 2. What is its conjugate? There is no I to replace. So, again 2 itself. So, that means if z equal to z bar, then the complex number is a real number. If it is a complex number, I will be replaced by minus I in its conjugate. So, for example, the conjugate of 3 is again 3. So, simply we can say, we can use A equal to or A bar equal to A, the conjugate of a number and the number both are the same. That means it is a real number. Now, let us solve some problems. The first one, if W equal to f of z is defined as z square for all z, find the value of W when z equal to 2 plus I, z equal to 1 plus 3i. So, the solution part, the first question, f of z is z square, and in the first question z is given as 2 plus I. So, that means f of z will be 2 plus I whole square. So, which is in the form of a plus b whole square. So, 4 plus I square plus 4i, a square plus b square plus 2 into ab. So here we know that I square equal to minus 1. So 4 minus 1 plus 4i, which is 3 plus 4i. So again it is in the form of a complex form, and here which is called the real part, and this is the imaginary part. Similarly, the second question, f of z equal to z square, where z is 1 plus 3i. So let us substitute that 1 plus 3i whole square, a plus b whole square again, 1 plus 9i square plus 6i, and 1 9i square. I square is minus 1. So minus 9 plus 6i. So minus 8 plus 6i. So again, this is the real part and this is the imaginary part. So all these are simple examples. Similarly, the second one, f of z is defined as z square plus z for all z. Find its real and imaginary parts. So first we need to find its real and imaginary parts. Also, we know that what is z? Z is x plus iy. So let us substitute that here. F of z is x plus iy whole square plus x plus iy. Now simplify this function. So x square plus I square y square plus 2ixy plus x plus iy. So which is x square, I square equal to minus 1. So minus y square plus x plus, here we can take I common from these two. So I into 2xy plus y. So this is the real part and this is the imaginary part. Similarly, also find the value of w when z equal to 1 plus I. Similar to the previous problem, let us substitute z equal to 1 plus I. Or else, already we have xy here. So we need to compare this with x plus iy. So x equal to 1, y equal to 1. Let us substitute here. F of z equal to, put x equal to 1. So 1 minus 1 plus 1 plus I into 2 plus 1. So these two cancel. So 1 plus 3i. So this is the value of f of z at the given point z. Now the third one. The function f of z is defined as iz plus 3z bar. Find u and v such that f of z is u plus iv. So here we know that z is x plus iy and f of z will be denoted by w, which will be in the form of u plus iv, where u is the real part and v is the imaginary part. So we need to find these two real and imaginary parts. So z is x plus iy plus iy. That implies what is z bar? X minus iy. Replace I by minus I. Now substitute these two in the given. So I into x plus iy plus 3 into x minus iy. So this is I into x plus I square into y plus 3x minus 3iy. And again I square equal to minus 1. Here we get minus 1. So the real part is 3x minus y and imaginary part, I take I common, x minus 3y. So which is in the form of u plus iv, where u is 3x minus y and v is x minus 3y. Also find the value of the f of z when z equal to 1 plus 4i. Z equal to 1 plus 4i. So similar to the previous problem, let us compare with this x plus iy. X equal to 1 and y equal to 4. Substitute that here. So f of z becomes 3 into 1 minus 4 plus I into 1 minus 3 into 4. So this is 3 minus 4 minus 1 and 1 minus 12 minus 11i. Similarly, show that the function f of z equal to xy plus iy is everywhere continuous. So we need to prove that the given function is continuous everywhere. Now first of all, what is the definition of continuity? So a function f of z is said to be continuous at a point z equal to z naught. First, f at z naught should be defined, and the limit as z tends to z naught, f of z must be equal to f of z naught. So we have, what is z? X plus iy. Then z naught will be x naught plus I y naught. Now we need to find the limit. So limit as z tends to z naught, f of z means limit as z tends to z naught, x naught plus I y naught. And what is f of z? xy plus iy. So that means limit as x tends to x naught, y tends to y naught, xy plus iy. Now for example, first if I apply as x tends to x naught, first the limit as x tends to x naught, then this becomes y tends to y naught, x naught y plus iy. Now again y tends to y naught, x naught y naught plus iy naught. Now what is this x naught y naught plus iy naught? So here we have z naught is x naught plus iy naught, and if what is the function here? F of z is xy plus iy. Then what will be z naught? X naught y naught plus iy naught. So which we got the same here, which is f of z naught. Not only this, for example, limit as z tends to x naught plus iy naught, xy plus iy. First if I apply y tends to y naught, then x tends to x naught on this function. First y tends to y naught, x tends to x naught, x y naught plus iy naught. Now apply as x tends to x naught, x naught y naught plus iy naught, which is again f of z naught. So in both cases the limit is equal to f at z naught. Hence given f of z is continuous everywhere. The next one, find the derivative of z square using the definition of derivative of a function f of z. So what is the given function? Given f of z equal to z square, and we know that what is its derivative? Directly we can find the derivative of z square is 2z, but we need to prove that using the definition of derivative of a complex function. Now what is the definition of derivative of f of z? Limit as delta z tends to 0, f of z plus delta z minus f of z by delta z. If this value exists, so we need to calculate this value first. So f of z plus delta z. Now what is the given first? First what is the given function? F of z is z square. Then f of z plus delta z will be z plus delta z whole square. Again a plus b whole square, z square plus delta z whole square plus 2z into delta z. So let us find this value. Now limit as delta z tends to 0, f of z plus delta z minus f of z by delta z. This is equal to limit delta z tends to 0. The first term is z square plus delta z whole square plus 2 into z into delta z minus what is f of z? Z square by delta z. So these two gets cancelled first, plus and opposite with opposite signs. So limit as delta z tends to 0. Now what remains? Here I can take delta z whole square is here. So delta z I can take common. So delta z plus 2 into z by delta z. So these two gets cancelled. Since there is no term in the denominator, particularly delta z is not present, now we can apply this delta z as limit delta z tends to 0. So if delta z tends to 0, I can put 0 here in the place of delta z plus 2z. So the answer is 2z. Hence the derivative of this is f dash z. If f of z is z square, then its derivative will be 2z. So that we can prove using the definition of derivative of a complex function. So in today's session, we have discussed about limit and continuity of a function of complex variable. Limit of function of complex variable. And also we have solved some problems on finding the continuity, whether the function is continuous or not, finding the derivative, and also finding the value of the complex function at the given point z equal to some z naught. In the next session, we are going to discuss about an important topic called analytic function. And the entire complex functions of complex variables are basing on this analytic definition of analytic function. So in the next class, we are going to discuss about an analytic function, and also we solve some problems on analytic function. This is for today's session. Thank you very much.